It's called an isoelectronic series. Consider, for example, N3 minus, O2 minus, oops, it's not two oxygens with one charge, it's one oxygen with a 2 minus charge. So F minus, Ne, Na plus, Mg2 plus, Al 3 plus. Which of these is the biggest, and which of them is the smallest? A clue for helping you to figure this out might come from the name, isoelectronic series. Iso means same, electronic means electrons. Isoelectronic means same electrons. These guys all have 10 electrons. So what do you think they have different? Well, they're different elements, so they have different numbers of protons. Okay, neon right in the middle has 10 protons. 9, 8, 7, 11, 12, 13. So the isoelectronic series is really, really simple. More protons is harder pull, fewer protons is less pull. So, biggest and smallest. To put it another way, you add electrons, something gets bigger, you take electrons away, something gets smaller. Positive ions, you would expect them to be smaller than negative ions, if they have the same number of electrons. Next up, we have ionization energy, or IE. Ionization energy is the amount of energy needed to remove an electron. Once again, we can explain this in terms of effective nuclear charge. We're talking about same sort of trend as atomic radius. Okay, you take an electron away from a neutral atom, you're basically trying to pull it away from the nucleus. The smaller the atom, the closer the electron is to the nucleus, the harder it's being held, the harder it is to remove. The further away it is, the easier it is to remove. So the general trend is like that. The biggest atoms have the smallest first ionization energy. The smallest atoms have the biggest first ionization energy. Okay. Now, I'm calling it the first ionization energy because if you have multiple electrons, you can remove multiple electrons. Okay, so the second ionization energy is the energy needed to remove the second electron, and so on. But that's just the general trend for first ionization energies. There is another trend you see, or I should say there are exceptions. Okay, you see jumps. You see places where an element to the left is higher than the element to the right. Okay, you expect it to get bigger going to the right, but sometimes, element X has a higher first ionization energy than element Y. And that's not what you would expect, generally speaking. But it's easy to explain when you look at the electron configurations. So let's compare nitrogen and oxygen. Okay, nitrogen has a bigger first ionization energy than oxygen does. You would expect oxygen to be higher because it is smaller. Okay, it's further to the right. The reason for this, like I said, is electron configurations. So helium, 2s2, 2p3, versus helium, 2s2, 2p4. Because we're talking about first ionization energy, we're talking about removing one of those 2p electrons. So let's take a look. Boom, boom, boom. 2p. 1, 2, 3. 1, 2, 3, 4. And now, it might be obvious. if you were paying attention back in lecture 25. The reason it's harder to remove the first electron from nitrogen than it is to remove the first electron from oxygen is because of resonance. The first electron that you take away from nitrogen is resonating with the two others. The first electron you remove from oxygen has no resonance, and it's paired up with another electron. Being paired up, it's got a bunch of repulsion going on. It's a little bit less happy. So oxygen, it's easier to remove that first electron. You see similar sorts of things, not necessarily as dramatic as with nitrogen and oxygen, but you see that sort of thing every time you're looking at a half-full subshell versus the element directly to its right. So, for example, manganese and iron. It's not as big a difference, but it's there. All right. Now, in a similar vein, instead of just comparing different elements, the first ionization energies of different elements, we can compare successive ionization energies within a single element. Okay? So we call this successive ionization energies. Okay? Meaning we can look at the first and the second and the third and the fourth and so on. So we look at oxygen again. How much energy do we have to put in to remove, the first versus the second, versus the third, versus the fourth, versus the fifth, versus the sixth, versus the seventh. All right. I have, sketched these out kind of roughly, sort of a guesstimate. But you can see there's a jump here, there's another jump here, and there's a huge jump here. So there's 1, 2, 3, 4, 5, 6, and 7. Why the jumps? Well, once again, we look at the electron configuration. Oxygen, 2s2, oops. Helium, 2s2, 2p, 4. So the first electron remove is this one right here. The buddied up, the paired up one, it's pretty happy to go. The second one remove, it's going to be sort of like nitrogen's first electron. It's got resonance going on, it's less happy, so that explains that first jump there. The second and the third, the third and the fourth, we're removing the last of the 2p electrons. So it's not, as huge a leap going from one to the next, okay? I mean, it is still increasing because there's less and less repulsion as you remove electrons, and the number of protons is staying the same. So it's harder and harder to remove each one, but it's not necessarily a huge leap. You get another slight jump when you move over to those s electrons, just because they're slightly closer in to the nucleus. But again, it's not a huge jump. Then you remove one of them, you remove the other one. And now, having removed 6 electrons, you've removed all of the valence electrons. Number 7 is ridiculously hard, because that one is core. Removing a core electron is incredibly difficult. Okay, removing electron 2 was harder because of resonance. But removing a core electron is absurd. Okay, you always get a massive, ridiculous, huge jump going from valence to core when you're talking about ionization energies. So when you're looking at ionization energies, when you're looking at successive ionization energies too, pay attention to resonance and core. Okay, those are the two things you really need to look out for. That's where you're going to see big jumps, unexpected leaps in ionization energies. And next up, we talk about electron affinity, also known as the zeroth ionization energy. This is the energy you get, the energy that's released when you add an electron. Now, because we're calling it zeroth ionization energy, you would expect it to act a lot like ionization energy. And that's largely true. Okay? You would expect it to increase just as ionization energy increases. You would expect it to be biggest in the top right and smallest in the bottom left. That is what you see, but you also get some complex and complicated exceptions. Once again, this has to do a lot with electron configurations. Okay. So we're going to tackle it in two different ways, these exceptions. First off, we're going to talk about left to right, then we're going to talk about going from top to bottom. Okay. Left to right for electron affinity. Okay. Because going from left to right, you are getting an increase in effective nuclear charge, the electron affinity should increase. You should get more energy out as you add an electron. And this is largely true, but you get three important exceptions. First off, the alkaline earth. Next up, the pnictogens. Finally, the noble gases. I mean, the noble gases, it should be obvious, okay? They don't want to react at all. That means they don't want to lose electrons, they don't want to gain electrons, they want to do nothing. They're nobility, they're lazy, okay? But the reason for this is exactly the same as for the alkaline earth and the pnictogens, okay? The alkaline earth have a full s orbital. The pnictogens have a half-full p orbital, and the noble gases are just completely full of everything. You know, any subshells they have any electrons in are completely full. S is full, P is full, D is full, F is full. Half-full subshells, completely full subshells, completely filled shells, those all resist gaining another electron. Okay, so the electron affinities for these are lower than you expect, okay, because they're resisting this new electron. Okay. The next trend we're going to look at is top to bottom for electron affinity. Now, this one, I don't need to emphasize the different groups as much because we're talking about rows. Okay. So going from top to bottom, you expect a decrease in electron affinity. Just because every row you go down, it's getting further out, it's getting further away from the nucleus, there's less attraction to the nucleus, so you're not going to get as much energy. And that's true. Okay. But, oddly, the second row, not necessarily of the periodic table, but of a group. So, second element of group is often bigger. That is to say, the electron affinity of the second element of the group is often bigger than the electron affinity of the first. So, for example, you have hydrogen versus lithium. You have beryllium versus magnesium. You have oxygen versus sulfur, fluorine versus chlorine, helium versus neon. Okay. We're comparing different rows, you know, row 1, row 2 versus row 3. But the second element in the group is what matters. Okay. So sulfur is greater than oxygen, chlorine is greater than fluorine, neon is greater than helium. And why is this? It's because of repulsion. When you add a new electron, you get the opportunity for more resonance, yes, depending on the configuration. But more importantly, you're getting more repulsion. Okay? And for a small element, okay, and the higher you are on the periodic table, the smaller the element is. Okay, so the smaller the element, the more significant that repulsion is because the electrons are confined to a smaller volume. So there's greater repulsion. So in the second row, the element is bigger so that repulsion is less. So you get that a sort of odd balance, repulsion versus resonance. Okay? So for the small elements here, the first row, repulsion wins. For the second row, resonance wins. Second row versus first row. Which is more important? Okay? So that is the big exception you see there, is that, and going from top to bottom, okay, is that the second row, or the second element in each group, I should say, has a higher electron affinity than the first. Very often. Not always. It's not a universal. And that does it for this lesson, this lecture, this section, and for Chapter 6. I'll see you next time.